So we're going to start off our discrete mathematics unit with sequences. And if you remember way back in the beginning of Algebra 1, we started the year off in Algebra 1 with sequences found in fractal patterns. And so now it's time to look at sequences in Algebra 2. Now sequences and these things called series are going to be super important in calculus. Actually, you can pretty much view all of calculus in terms of sequences and series. Now, we're going to first talk about the infinite sequence. Basically, you have to think of a sequence as a function whose domain is limited to natural numbers. So 1, 2, 3, 4, 5, 6, so on and so forth, basically positive integers. That's the domain, and that's how you get a sequence. So the function value, we call the terms, a sub 1, a sub 2, a sub 3, a sub 4. Notice they start with the first term, that is a sub 1. So you plug in a 1, not a 0, a 1 into a sequence. And of course, if I limit the domain to be just some n positive integers, I no longer have an infinite sequence, I have a finite one, meaning one that ends. So when you see something like this, this is the rule to generate the terms of a sequence. And remember, for sequences, you have to start with n equaling 1, and then go, of course, to n equals 2, and n equals 3, so on and so forth, to generate the term of the sequence. So I have 3 times 1 minus 2, 3 times 2 minus 2, and then 3 times 3 minus 2, which give me a 1, a 4, and a 7. So the sequence that this rule describes is the sequence 1, 4, 7, 10, 13, dot, dot, dot. You're just adding 3 each time. And this kind of sequence we saw in Algebra 1, and we related it back to linear functions because, well, this kind of sequence is kind of like a linear function. Now, we didn't look at sequences like this next one, a sub n equals 3 plus negative 1 raised to the nth power. And I chose this example because it's just kind of neat what happens with this sequence. So if I choose a sub 1, I get 3 plus negative 1 raised to the 1 power, which is just 2. And if I choose 2 as my next term, oopsie, 1 second, I get 4. And if I plug in 3, I get 2, and if I plug in 4, I get 4. So this sequence is sort of a novelty in that it gives you alternating numbers forever. And that's because, of course, the negative 1 is being raised to alternating even and odd powers, which changes it from plus 1 to minus 1. And in this sequence, that negative 1 to the nth power is sort of some trivial little thing. But in this next sequence, it's actually quite important, and it generates a special kind of sequence. So here's the rule I have. A sub n equals negative 1 raised to the n plus 1 power all over 2n minus 1. And I want to see what's happening with this sequence, so I'm going to find a sub 1, a sub 2, a sub 3, and a sub 4. So what this rule generates is a sequence whose successive terms alternate from being positive to negative, and we call this an alternating sequence. And if you ever have a sequence that changes signs, like this one from positive to negative to positive to negative, that means someplace in the sequence is a factor with a negative 1 raised to some power. And of course, you can change this index so that it starts with either a positive or negative. If you start it with an n plus 1, in this case, it started off with a positive. And if I just made it n, I'd have it start with a negative. And this is going to be important for when you are asked to write these types of formulas for the terms of a sequence. Now, speaking of writing rules for sequences, if you want to define a unique sequence, meaning one sequence that goes on forever, no doubt in what it is, you have to give someone the nth term, meaning that a sub n rule. Otherwise, you don't have a unique sequence no matter how many terms you give someone. And we're going to consider this sequence. 1/2 1/4, and 1/8. And it looks like what's happening in this sequence is you are taking powers of 2. So it looks like it's 1 over 2 to the n is what a sub n equals. But that's not actually the case, because if I only have 3 pieces of data, then I could come up with any number of different formulas that's going to actually generate a 1/2, a 1/4, and a 1/8. For example, I can come up with this rule for a sub n, and it's going to give me 1/2, 1/4, and 1/8 in the beginning. But of course, after this term here, everything changes. So if I want a unique sequence to be defined, I have to give you the nth term, not some terms of the sequence in the beginning. Now, the first rule that someone is going to come up with for this sequence is, of course, 1 over 2 to the nth power, because it's the obvious one. And the one that you figure out, okay, given a couple of terms of a sequence, is called an apparent formula, right? So if you assume, or basically when I ask you to write a rule for a sequence and I give you a couple of terms, you figure out a pattern and you assume that the sequence is going to continue in the pattern that you figured out. And the rule that you write for it is an apparent formula. So if I ask you to write an apparent formula for the terms of a sequence, I want you to figure out the pattern and write the rule for the pattern that you figured out. And now that doesn't mean there's only one right answer for this either. There's going to be an obvious answer like the 1 over 2 to the n, but someone else can come up with a different answer that is equally as valid. Now remember, recursion in Algebra 1 is kind of like the natural way to describe a pattern. You tell me what you start with, and you tell me the rule to generate each sequence. So if I define a sequence that way, I'm defining it recursively. So this is where the definition requires one or more of the first few terms, and all subsequent terms are defined using previous terms. And of course, the most famous example of a recursively defined sequence is this one, where I say a sub 0 is 1 and a sub 1 is 1. And what this notation here is telling me that the a sub n term was the term before that plus the term before that. And I have to give the criteria where n is greater than or equal to 2, which generates this sequence: 1, 1, 2, 3, 5, 8, 13, ... And we know this as the Fibonacci sequence. And this is a recursive definition. And recursive definitions are easy to spot because in the rule, you'll see a sub n's in it. Now, something we avoided in Algebra 1 altogether, but I know you talk about in like 6th grade math because it's kind of a fun thing, and that is the factorial. Factorials become much more serious in Algebra 2 and beyond. So this is the definition of factorial. If n is a positive integer n factorial is defined as n exclamation point, and then it's 1 times 2 times 3 times ... times n minus 1 times n. Now, as a special case, and remember this special case, we define 0 factorial as 1. One thing I need to remind you of, and you think in Algebra 2 I wouldn't have to remind you of this, but you need to follow the order of operations. Because 2n factorial is very different than the quantity 2n factorialed. Because this here is the same thing as 2 times n factorial. And if I expand this out, this is 2 times n minus 1 times n minus 2, ... all the way down to 1. So it's just twice n factorial. Whereas this thing here is I'm doubling the n value and then taking the factorial. So this one is 2n times 2n minus 1 times 2n minus 2, ... down to 1. So one thing that's you're going to have to do is you're going to have to learn how to simplify factorials. And you don't just, you could just type this in your calculator, but if I make these numbers really big or if I make them variables, you can't. So let me show you the technique for simplifying a factorial, right? And you're going to need this when you do probability later on. So here's the technique. You kind of expand until you see factorials that will cancel out. So in the case of 8 factorial, I know 8 factorial is 8 times 7 times 6, and then 5, 4, 3, 2, 1. But I notice in the denominator that I have a 6 factorial. So instead of writing all these out, I can just cancel the 6 factorials. And 2 factorial is just 2 times 1. And it just makes life a lot easier to be able to cancel off those 6 factorials. Now all I have to deal with is 8 times 7 over 2 times 1. So who cares about the 1? That cancels to be a 4, which gives me a 28. And honestly, you can do these faster than you can type them into the calculator. Now here's where it's going to be useful. When I have things like n factorial over n minus 1 factorial. And what is this? Well, n factorial is n times n minus 1. Oh, hey. And then it's going to be n minus 2, n minus 3, n minus 4, all the way up to 1. But then I can just realize that that's just n minus 1 factorial. And then I have the n minus 1 factorial down there. Those guys cancel, and I'm just left with n.